The objective of this heat transfer project is to analyze the effect of varying the temperature of a heated 3D printer bed on the cooling rates of the plastic as it's pressed out of the extruder. This project will consist of two parts, the first being an experimental portion. For the experiment, I measured the cooling rates of PLA and ABS plastic at various bed temperatures and plotted those versus time. For the analytical portion, I did transient conduction analysis using the lump capacitance method for the filament being deposited on the bed and how fast that would cool with conduction from the bed and convection from the surrounding air. So a little bit of background on this project. If you've ever 3D printed before, particularly with ABS filament, you know that it's important to have the ability to control your bed temperature because as the plastic cools, it shrinks. And with filaments like ABS, if it shrinks too quickly as it's deposited, it can cause warping, as you see in these pictures here. So a higher bed temperature will slow down the cooling rate. This will keep the polymer above its glass transition temperature for a longer period of time, and this will improve adhesion to the surface. So looking at 3D printing from a heat transfer perspective, you have the hot filament being deposited on a printing bed, which in the case of my 3D printer is made of aluminum. Now that printing bed is at a different temperature than the filament. It's a lot colder. You can change the temperature, but as a rule, the heat will be conducted out of the filament and into the print bed. How fast that occurs is a function of the temperature of the printing bed. So you have the heat flux due to conduction going out of the filament into the print bed, while at the same time you have convection coming off the top of the filament. This is typically free convection if you're not using a cooling fan. However, you can add a cooling fan to the process to introduce some forced convection and increase the cooling rate. So conduction from the heated bed and convection from the surrounding air cause rapid cooling to occur. In order to measure the cooling rates as the 3D printer deposited the filament, I set up a LabVIEW VI to measure temperature over time and plot it to an Excel file. I then set up the 3D printer to print a straight line from left to right. As the printer would print, I would insert a thermocouple just behind the extruder to take as high a measurement as possible for temperature to start out. The hope behind this was that it would give me a wide range of temperatures over time to do data analysis on to see how fast the filament was really cooling. This experimental procedure was repeated 5 times for each bed temperature and done for each type of filament. Now, after recording this data, I needed a way to compare the cooling rates. The best way to do that was to establish a common temperature range to compare the cooling rates at, much as we did in our transient conduction lab. Now, the difficulty came because the ranges for polylactic acid, the PLA filament, were so small because at the lower bed temperatures, the cooling would occur too quickly to pick up on the thermocouple. By the time I inserted the thermocouple and it registered the temperature had already dropped significantly. This left very little range to compare. However, for ABS, we got a much better result, and it's clear that as the bed temperature gets hotter, the cooling rate decreases and the cooling time increases, allowing for better adhesion to the build plate. For the analysis portion of this project, I attempted to use lump capacitance transient conduction analysis. However, this proved ineffective. After solving the differential equation using conduction and convection as the heat going out of the system, it turned out that the temperature versus time was inaccurate compared to the experimental data that was obtained. The inaccuracy observed in the theoretical analysis for predicting the cooling time can be explained possibly by two phenomena. One of which is the fact that the plastic filament, both PLA and ABS, have a non-constant thermal conductivity, much like other materials. That means that their thermal conductivity changes over temperature. And since we have such rapid cooling, the conductivity is changing rapidly. Now, the conductivity is not represented by the graph shown, but for many plastics it is similar. It's non-linear. It has a certain point at which the conductivity peaks and then drops off, and that's usually near the glass transition temperature. The other possible explanation is the thermocouple itself. Since our system, our control volume, if you will, is so small, being a small piece of filament that's only 0.3 millimeters thick, introducing the thermocouple and asking heat to be transferred to the thermocouple to induce a voltage that we can measure and convert to temperature may skew the results. Sort of like the Heisenberg uncertainty principle, the very act of observation changes the outcome.